In this video, we'll be going over the bottom-up 2D matrix approach of maximal square. Let's go over the thought process. So let's convert the top-down memorization approach to a bottom-up approach. Now, where do we start? In the memorization approach, we have cached the current cell RC with the length of the square. This means we can create a 2D matrix length to keep track of the length of all the squares with the top left corner at RC. Now let's go over the pseudocode. So we're going to create a 2D matrix length to keep track of the length of all squares with the top left corner of RC. Now before that, let's do one more thing. Let's validate the input parameter. If the input matrix, if matrix is empty, then the area of the largest square will be 0. We can just return 0 here. And then we can create a 2D matrix length. Then the rows represents R. The columns represent C. And the values represent length. Now I want to iterate through the rows from matrix.length -1 to 0, denoted as R. We're going to iterate through the columns from matrix R.length -1, which is the last column, to 0, denoted as C. If the current cell, if matrix RC is equal to 0, this means the length of the current square will be equal to 0. So we can just continue to the next iteration. Because the default values inside our length matrix is 0, so we can just continue on. Now we want to set length RC to the minimum value between length of R plus 1 C, which is the length of the square at below, and length RC plus 1, which is the length of the square to the right, and then length R plus 1 C plus 1, which is the length of the square to the bottom right. You can say to the bottom. Now we want to increment length RC by 1 to account for the length of the current square with the top left corner at RC. And one more thing we need to do is create a variable, max length, to keep track of the largest length of all squares. Now we want to update max length if the length of the current square is greater. So if length RC is greater, then we can return max length square, which is the area of the largest square. Now let's go over the time and space complexity. For the time complexity is O of mn, where mn are the number of rows and columns. This is the nested for loop. Now the space complexity is also O of mn. This is because of our length matrix. Now let's go over the code. So we'll first validate the input parameter. If the input matrix is empty, we can just return 0 as an area. We're going to create the following variables. Our current m is the number of rows, and then n is the number of columns, and also the max length, so the length of the largest square, initially 0. Then we can create our 2D matrix length to keep track of the length of all the squares with the top left corner at RCs, or each cell. Then we iterate through the rows from the last row to 0. We can iterate through the columns from last column to 0. if the current cell contains a 0, this means the length of the square is equal to 0. So we can just continue to the next iteration. Now, for the length of the current square, we first have to find the minimum length of the squares to the right, to the bottom, and to the bottom right. So let's do the math.min. The squares, the first square is to the bottom, so r plus 1c, and also the length of the squares to the right, so c plus 1, and also to the bottom right, so r plus 1, c plus 1. Then we can increment it by 1 to account for the length of the current square. Then we can update max length if the current length is greater. Then we can return max length square, which is the area of the largest square. Oh, we need to make it m plus 1 and m plus 1. Because when our square is out of bound, the default value will be equal to 0. So we can just set it to m plus 1, m plus 1. Let me know if any questions in the comment section below.